I think we should start. And thanks for everyone for coming to the astrophysical seminar today. And our speaker is Luca Comisso. And Luca obtained his bachelor and master degree from Polytechnic University of Milan, and finished his PhD degrees at the Polytechnic University of Torino, and right now he is astrophysicist, plasma astrophysicist at the Columbia University, and he is expert in plasma physics and astrophysics. So I think today he will give a very good about the plasma physics. Please go ahead, Luca.
Thanks for having me. The talk that I'm giving today is about some general mechanism of particle acceleration in a highly magnetized turbulent environment. And the structure is a bit as this. First, I'm going to give you some examples of particle energy distribution that are produced with some form of acceleration, essentially. I give only some cases that are going to be ubiquitous in different environments that just set the stage. Then I'm going to tell you why I think that turbulence is going to be quite ubiquitous in such environments, so it's something that you should expect. And then I'm going to explain some mechanisms of particle acceleration that will be fairly general. And then I will discuss how those mechanisms will produce non-thermal distribution of particles, and I would like to focus at least in one very important example that are some very recent results where we think that such mechanisms could explain potentially the generation of ultra-high energy cosmic rays. Then I've been very ambitious and optimist, so I do not know if I'm going to be able to get to the pitch angle anisotropy of particles produced by turbulence. But anyway, we can discuss that if you're interested while I'm here, that I think is very, very important for interpreting the radiation. And then just a few takeaway messages. So the very, very first and probably more well-known distribution of essentially non-thermal particles that we have is like essentially the energy spectrum of cosmic rays. Here in this plot is the energy flux of cosmic rays in the y-axis as a function of energy. In the x-axis, you can see that they span a very broad range of energies. And there are some features. At the zero order, you see that there is an extended power law that goes as energy to the minus 2.7, very broadly speaking, up to some feature here that is called the knee, where it steepens and we go like energy to the minus 3.1, and then there is some other feature, some sort of bump when you have these very high energetic particles here. These are essentially considered what we call essentially ultra high energy cosmic rays, and they are believed to be of extragalactic origin. They cannot otherwise even be confined in our galaxies. Here at the very, very left side, most of the contribution comes from the sun. And then we believe that this initial part of this loop, the most of the contribution comes from supernova remnant and shocks accelerating those particles. There are quite some issues to understand what is happening to the knee. There are many other tiny features that with increasing statistics, we can see many other features here. I'm going to zoom in few things happening here, but I just want to say that this plot is very rich and is a good thing, because by being very rich, we can actually try to decode as much as information we can from the astrophysical sources. But there is a complication that is actually a huge complication, is that these particles are accelerated somewhere and they are charged, and they, because of the magnetic fields, they go around and we cannot really point down from where they come from. So there is quite a bit of reverse engineering to be done here. So my goal is to understand with the physics, plasma physics, what happened in the accelerator, to put some significant constraints on understanding why we see these particles. There are cases that are a bit more lucky, where we can actually probe in situ the distribution of non-thermal particles. And indeed, we have the sun that is weak in the standard that you've seen before as accelerator, but it is close by and accelerate particles to non-thermal energies. These are very recent results for the Parker Solar Probe, that is the probe that we've been able to put closer in orbit to the sun. And you can see here there are some solar energetic particle events. Essentially, these are protons. Here in this plot, there is the proton fluence as a function of energy for 6 different events. And you see that these protons follow some power law distribution to a fairly good degree. And at the end here, they stop here the energetic of the proton, mostly because there is the limit of the instrument. They have lower energy, but you see this distribution cannot be explained with a Maxwellian distribution. So there is some mechanism that is producing them.
What is this power law exponent?
It is fairly steeper than -2 in energy, maybe between 2 and 3-ish, essentially. It's something quite common, but it highly depends on the event. They can be even steeper than that.
They seem to be different for different events.
Yes.
What do we take away from that?
It's very good. We actually need to know what produced them first. Actually, I just give you a first insight. Most of them are actually accelerated as shocks, but actually they depend also on how they are fed, those shocks. In a sense, in some cases, you need a suprathermal population of particles, otherwise some sort of shock will be inefficient in producing those power law. So actually, it's a combination of how you feed the shock and the outcome of the shock, and then of course other aspects like Mach number of the shock and so on. At this point, I just want to emphasize that they are quite common, and we want to actually reverse engineering what is happening.
So, but the number of the measured particles increases from event to event, right? Or
Yes, correct.
it's like different
yeah.
approaches to the sun, or this is just some physical event somehow?
Or it's a combination of where the spacecraft is located, because they're also, for example, if you are very close by, you can intercept a lot of particles, but if you are in a slightly different position, essentially some particles will be out of the cone of the single instrument that is placed there. So it's a combination of that. You again, you need to reverse engineering to understand what was the original number of particles being accelerated. But in any case, also the shocks, they will accelerate, they will have different efficiency in the number of particles that are accelerated. So they will not produce always the same number of accelerated particles. Another, let's say, actually, most of the cases, actually, we see photons. Essentially, we are not that lucky to detect the particles. And so here, I showed two spectral energy distribution. Here, probably the most studied object in high energy astrophysics, the Crab Nebula. And you see the spectral energy distribution in this case, nu and ergs over seconds, and here is in frequency in the x-axis. And you see that there are some ranges that are very well described by a power law. In this case, actually, the first hump is like thought to be due to synchrotron radiation, and the second one inverse Compton. And to produce this power law in the spectral energy distribution, you need, at least the current most common explanation is that you need a power law in energy of the underlying particles. You can see how beautiful these power laws are. And similarly, you can see this from other objects, like, for example, laser jets that are essentially jets that are pointing to us, and the jet outshine the remaining part of the active galaxies. And here also you can see this structure, even if the power law are less extended. Again, to fit that, you need some non-thermal distribution of particles. That typically, many times, is in astrophysics is a phenomenological assumption, but what we want to know here is, for first principle, what kind of process produced them, because then we can infer also the property of the environment. So at the zero order, what we want to know is how some thermal distribution, and for example, in this case, let's say a Maxwellian, that is the most likely distribution for a system that is in thermal equilibrium, how that will develop some other features that they are a complication, but from my point of view, actually is a richness, because otherwise, if all we were to see were thermal distributions, we will not be able to extract much information for the astrophysical system. So luckily, we have some other features, and if we understand them, we can actually get to know a bit more what is producing them. So we want to see what kind of process produce what kind of features in the distribution of the particles. And physically, like in a plasma, there are different ways to produce non-thermal distributions. Depending on how much creative you are, you can add several other processes here. But essentially, some processes are very common and they occur in quite ubiquitously in different conditions are the ones that I actually put some picture here. that are shocks, magnetic reconnection and turbulence. Here I should have had collisionless in front of all of them, because if the system is enough collisional, then of course the distribution will Maxwellianize, and so you will not see those features. So I dropped collisionless, and it's like agreed that I'm always going to discuss about collisionless processes. Shocks tap energy from the bulk flow, while both magnetized turbulence and magnetic reconnection tap from energy from the magnetic field. And I'm going to discuss mostly magnetized turbulence, but in reality, I'm going to discuss also reconnection, because the two comes a bit together. So if you have a large enough astrophysical system, turbulence will also produce reconnection layers inside that. And the case of the converse is also true. If you have a large enough system where there is a large scale reconnection layer, also will produce turbulence inside. But I'm focusing on the previous case. Let me introduce first what I mean when I say that a system is magnetized, and actually when a system is extremely magnetized, because you see some of these parameters coming in several times. So the main parameter that I'm discussing here is the magnetization parameter sigma. That is essentially the ratio between the magnetic energy density and the rest mass energy density. If the plasma is very hot, relativistically hot, you can also add the enthalpy in the denominator and to make it more general. But essentially, this is like the cold plasma definition. And this is also related to, maybe some of you are more familiar with the plasma beta parameter, that is the ratio between the pressure, thermal pressure, and the magnetic pressure, beta here, that are related to the temperature. So clearly, as sigma goes up, beta goes down. And we typically classify in high energy astrophysics relativistic regimes and non-relativistic regimes in terms of magnetization in this case. So when sigma is below unity, the advent velocity becomes significantly less than the speed of light. And these are kind of plasma that you are more commonly familiar close to the Earth, like the sun corona, or experiments here, lab experiment we have here, actually also PPPL here has several experiments, they are all in this regime. But when sigma is greater than unity, then the speed of the advent speed approach the speed of light, and imagine that the bulk motions of the plasma, imagine that is turbulent and is following the advent speed, then it means also that the motion of the turbulent plasma will become relativistic. Another way to see it, this is not the only way to see it, is the following, that sigma essentially tells you what it is the mean energy per particle. So even if at the beginning the plasma were non-relativistic, and you share democratically the energy and you dissipate all the magnetic energy to your particle, a non-relativistic plasma will become an ultra-relativistic plasma. So there is a large reservoir of energy. Many of the things that I'm discussing actually are quite general, but for some cases I'm going to specify the ultra-relativistic regime where I say where sigma is greater than u, because it's particularly interesting, specifically if you want to accelerate ultra-energy cosmic rays. So why should we care about this environment? Because I argue that in several systems, especially compact objects, close to the compact objects that are my preferred ones, you have a lot of magnetic energy that is a reservoir for your particle acceleration. For example, here, one of my preferred ones is like the environments close to black holes. Typically, if they are accreting, it's a bit of a mess. But in general, some general features that you typically have is like an accretion flow, an accretion disk, maybe thin, maybe thick, but essentially you have some sort of accretion where the magnetic field energy densities believed to be not that dominant, but it depends on the models. And then you have typically above them some corona where essentially the relevance of the magnetic field typically get higher, and the beta parameter get less than unity. You may have winds that also may be significantly magnetized. You may have jets that are very highly magnetized. Typically, if they are launched with some mechanisms like point impact dominated, like Blackford-9 model, for example, essentially they start with sigma much greater than unity, and very, very close by here there is a question mark. Still, we don't know that much, but actually also with Event Horizon Telescope we are getting closer and closer and getting information of the structure of the magnetic field with polarization measurements and so on. And also here it's believed to be significantly magnetized. So then I want to make another case. Why should we consider turbulence? The fact is that in astrophysical system, the system are very large in the sense that the scales where you inject energy into the system are way larger than the plasma dissipation scales. So because of that, when you have smooth gradients, you typically don't tend to dissipate energy. And so the system self-organize itself in such a way that form a broader range of scales that cover from the large scales up to small scales where gradients are strong. And even if the dissipation processes, the dissipation terms in your governing equation are small, because they multiply very strong gradients, then they become important. So the system self-organize in this way at the zero order, even less possibly the picture of turbulence, something like that. You have some large scale fluctuation that break out to smaller fluctuation until they dissipate. You may have still inverse cascade, you may have no local transfer and other complication, intermittency, but let's say that you have this flow of energy from large scale to small scales. And just to give you an idea of how the separation scale it is, I just put some numbers taken, for example, here there is a rendering for jet, but let me specify this for a corona. The injection scale that is at least like the Schwarzschild radius is going to be 2 × 10⁻12 meters, but the largest of the kinetic scales, taking here the proton radius, is like 5 × 10⁻³ meters. So there is a 9 order of magnitude of difference here, at least, that need to be covered. And just for reference, the mean free path for protons is much, much larger than all these scales, so the system is collision. So you expect, there is no reasons to believe that there should be any Maxwellian distribution here. There are not the conditions to have that.
How do you calculate the kinetic scale there?
This one, it depends on the temperature of the plasma, that is inferred by even here some radiation measurements coming from different sources. One is also Event Horizon Telescope collaboration, of course, that will imply also knowing the pitch angle and some other aspect, but assuming that all particles have isotropic pitch angle, you can reverse engineering and came out with a temperature. The previous picture was clearly not, didn't show some anisotropy, but if you have the magnetic field, actually you can stretch some direction, and typically dissipative like structures in MHD, they don't have the same shape as in standard neutral fluids, where the typical dissipative structure in neutral fluid is like a filamentary one, but in the MHD case, you have like more like ribbons-like structure. And if you want to see it like a ribbon-like, if it is cut just in the right way, it's like a current sheet, like this is like a cartoonish version of a current sheet that typically, when the field lines are just the right orientation, they reconnect. And so they change the topology, ideal MHD, that will imply having electric field plus velocity, maybe depending on the unit, divided by C, times the magnetic field, it will be 0. But in this region where the current is very strong, this is a very bad assumption. And essentially, relaxing this assumption allow you to change the topological configuration locally here, and it will allow you to decrease the magnetic energy, free magnetic energy that was available in these gradients here in the structures to the plasma. This, we think, is the mechanism that starts the acceleration process. So when particles are highly magnetized, they cannot experience large variations, so they cannot experience the fluctuation in turbulence, they are highly magnetized. But because there are these regions where ideal MHD breaks down, they can give an initial energization to those particles that then, when they start gyrating on larger scales, they can start sampling larger variation of turbulence, and then there is typically is taught a stochastic process of acceleration where scattering among the fluctuation you increase energy. This is a very cartoonish picture. So actually the point is make it very quantitative such that you can make exact predictions. For example, what will be the time scale of this acceleration? Can particles get to these energies and so on? So then if you want to make it very quantitative, then it becomes, that's the hard part. I just give here some collection of questions that we want to address. They could be longer than this list, but I just want to give you a first flavor of what we try to answer in general terms. You have a cascade and you want to know where the energy is going, if it's going into thermal species or non-thermal ones. Then you want to know if it's going into ions or electrons. And ions here, you may even have different species of ions. You want to know if you develop non-thermal tails, for example, with a power law description, and what will be the slope of such a power law. What will be the maximum energy that you can reach where you have a cutoff? What will be the radiative efficiency in the system? So is it going to radiate very quickly on, for example, on time scale comparable to the acceleration 1 or not? For example, what will be the spectrum of the emitted radiation from here? You will have complication if we get there, like pitch angle anisotropy and so on. I may even add others, for example, what would be variability due to intermittency and so on. So the list could keep going. But these questions are fairly basic and they are, for relevance, I want to specify for different systems. So, so they are quite, so we need to answer those questions if you want to actually reverse engineering using physics, the radiation that we see. To do this, at least there are different ways to do that. The approach that I will consider it more first principles is to solve essentially the Vlasov equation for the particle density Fs for with S a given species that is defined in a position X and momentum P and evolved in time T. Here the right hand side is 0 because we are neglecting collision, so that get the name of the Vlasov equation. And of course, gammas here are the Lorentz factor of these particles, and you have a given force. The simplest possibility is the Lorentz force, but for example, imagine that you have a radiatively efficient system. You need to add also, for example, other contribution like Abrandir Lorentz force, so you need to have the radiation reaction and so on. You may even have gravity effects here. At the 0 order, let's say the Lorentz force. And this is coupled with the Maxwell equations that evolve the electric and magnetic field, and the source terms are computed using the particle density from the Vlasov equation. If you want to solve this system, actually it's quite expensive, exactly as it is. So one computational efficient way to solve it, if you, for example, are not that interested in a linear stage of an instability, something that has very little noise, is to actually solve the Vlasov equation along characteristics. That essentially is like solving for the particle trajectories of single species particles, here electrons and protons. These allow you to have a computational gain and solve large-scale systems that we believe are astrophysically relevant, at the expense, for example, of some noise that, for example, if you want to bypass linear instabilities, or we need to use a lot of particles to resolve them and kill the noise, it's a very good compromise. So I'm going to use this method to solve the problem that I was discussing before. This is like how one of the field of turbulence look like from this large scale simulation. This is I want to specify here that is particle in cell turbulence, and this is like a slice of the turbulent domain across the mean magnetic field. And here what you see is the current density in the out of plane direction. And for the ones of you that are familiar with MHD simulation, that looks fairly similar. So I just want to emphasize that we capture some last cage properties of the flow, but we are not solving fluid equation here. We are just solving for the particle trajectories. And for the ones of you that squeeze your eyes, you can see that there are some plasmoid-like structure that form in these current sheets. And I'm gonna zoom, for example, in one of those current sheets, just to give you an idea of how these structures look like. Now, I just take a tiny portion of the domain, and I have 5 different slices that are at different coordinates along the mean magnetic field. So you can see that there is some magnetic field component preferential in this direction, and I highlight some field lines that thread these current sheets. And you can see that they form these flux rope structures that is like kind of the 3D equivalent of the 2D cartoonish that I showed you before, and they are typically representative of reconnection going on. Clearly 3D is a bit more difficult to picture it. Yes, please.
Are you sure that this is not the compression of the field lines? It's just will be large.
It's good question. The fact that we need to do different slides at different time, and if we see that change of reconfiguration of the field line, we can be sure that it's magnetic reconnection. In reality, this is a very deep question. Actually, it's not that easy to establish reconnection is going on, because, for example, there are also other consequences of reconnection. For example, I should show you, for example, if there are general outflows here, if it is associated magnetic dissipation, and so we have done that check. It's just that it is not all over plotted in this plot. It's a very good point. And actually, I want to point out that there is not a general measure of reconnection going on in 3D. So while in 2D is very easy to establish if reconnection is occurring, and you can measure. So you can, if the world were 2D and we can have an algorithm that we put in a spacecraft, and the spacecraft will be able to recognize if there is reconnection going on or not. In 3D is not possible, or at least there is not such a definition. So it's mostly based on cross correlation of different quantities. In this case, the simpler one would be also to add the outflows, the generated outflows here, and dissipation measurement like J dot T would be the very standard one.
What's the scale for this reconnection region?
A good point. Essentially the cross, so the transverse size of this kind of sheet is a bit above the electron skin depth, but the length is closer, is a significant large fraction of the correlation scale of turbulence. So essentially those are essentially intermittent current sheets, so they are structures that are more prominent than the others. I'm going to give you a bit of statistics now in the few next slides.
This is became turbulent.
Tell me?
This is became turbulent.
A good point. This is also became turbulent. I'm going to give you another, just this case, a 3D rendering of the same domain. I just want to emphasize that the structures, how they are from different scales, at least from the one that we can capture in our eyes. This is still the current density. It's not in the Z direction, but is the mean value. And here I just remove some values that were below a threshold in terms of root mean square value of the current density. And now in the domain, we are actually going into the direction along the fields, and you see that they are stretched along the mean magnetic field direction. And you can see there is a sea of structures, some that can get closer to the correlation length, that is essentially 1/4 of this domain, 1/3. And then they cover some other smaller scales. So just to make sure that some of the properties of the turbulent make sense, at least with what we can measure. For example, the best experiment that we can have access, because in high energy astro we cannot put probes, but is the sun. Here in the right, I put the power spectrum. This in the inset is like the magnetic field fluctuations, and I put the power spectrum computed from the peak simulations. In blue is the magnetic power spectrum, and in red is the velocity spectrum. And you can see that at large scales, they kind of resemble the Kolmogorov-like scale. Here is like Goldreich-Schrieder-like, where the wave vector is in the perpendicular direction, where the cascade is more vigorous, and it follow like k to the -5 divided by 3. Then it steepens as soon as it gets the largest among the kinetic scales, in this case, the ion skin depth, if beta is below unity. It steepens here something that is close to k to the -2.8. And then it steepens again. It's not clear if it is a power law or not. And you can see here in the left what would be the power spectrum. Here is the magnetic power spectrum observed from the solar wind. This is one single spacecraft. So what it detects is a spectrum in frequency. But with the with the Taylor hypothesis, you can link the wave number to the frequency if you know the velocity of the wind. And you can assume that this F is essentially wave number. And in this case, again, at large scales, like MHD light scale is like -1.7-ish, close to what we get. Then it steepens about -2.8, close to what we get. And then there's something that here is like approximated with some exponential cutoff at very low scales. But of course, the power spectrum is a very reduced information of turbulence. It contains very little information, so one can check things at higher orders. In this case, you can look at 5-point structure functions. And these again, in the left, is the measurement from the solar wind. This is from our simulations, and we consider, at least for this plot, structure function up to the 5th order. And then in this case, we consider 5-point structure function that are better suited if you have strong, steep power, essentially power spectra. They can capture better the trends and the features. And we can then analyze what would be the intermittent properties, if any, of the flow. And in the left here, you can see observations, and here I'm showing you what is the scaling exponents here as a function of the moment of the structure function m. And in the left is like the plot for the solar wind, and in the inertial range of the turbulence here is the inset, and is in the ion kinetic scale range is in the main plot. And this is for 3 different components of the magnetic field in the inset. You can see that if the process were to be self-similar, you will expect a straight line. And in the inertial range, actually, it bends significantly after the third moment, essentially. But this is much less prominent in the dissipation range. We see a similar feature from our simulation where in the MHD range, so large scales, you see that there is a significant curvature showing departure from self-similarity and intermittency. Essentially, it's like a measurement, essentially, of intermittency here for one component of the magnetic field, like perpendicular to the mean field, that is well approximated by the log-Poisson model, even if we don't have a fully developed understanding of the model itself. But in the ion kinetic range, essentially the intermittency is less pronounced, and it is closer, even not yet linear, but closer to linear. That is something that we are learning from the spacecraft, even if we don't have really a satisfying model to explain the intermittency of those scales. Actually, not even in MHD scales.
What's steepening of magnetic field spectrum could that because part of magnetic energy is used to accelerate it?
This is actually my interpretation. Is current under development. So the effects of magnetic reconnection in turbulent cascade is also my interpretation that at those energy you trade magnetic energy to bulk velocity. So essentially, that is a reason for the steepening. There are different theories that typically the overall understanding is that at the scales where reconnection kick in, the magnetic field steepens with respect to the standard predictions. Essentially, the turbulence become more vigorous. What is the precise slopes and if it is even a power law also, that is still not clear. I want to give you an initial feeling of why these intermittent structures are important, because I was claiming that reconnection is important to inject particles, and this is just a visualization. For this, to visualize it, I actually use a 2D simulation, just for simplicity in the visualization. What I'm going to show you is the development of the turbulence series, like what you see is the out-of-plane current density. And this is like a zoomed region close to one particle. And then here in the top is right is the Lorentz factor of such particle. And you can see that something happened at this time scale where there is a significant increase of the particle energy. And then there is again an increase, but at a lower pace. Here you can see current layers form. The particle is here. Look at now what happened. Particle goes between this big flux rope. It was kicked, and I just want to emphasize that flux ropes actually had a reconnection layer in between. And to show you, actually, I'm gonna stop here. You see, for example, to give you a feeling, you see that there was this plasmoid being ejected in this current sheet. So this plasmoid is a feature that occurs in reconnecting layers. You may have multiple ones if your domain size is much larger. This is not large enough to accommodate a large number of plasmoids, but this is like a signature of reconnection occurring between these two parts of the plasma trying to merge each other. And actually this is coincident indeed with the particle gaining a lot of energy here. Of course, this is one particle. You may not fully believe in one, so now I give you 10 particles. I'm proving a bit on the statistics. And you can see that for 10 different particles that are selected to end up in different energy beams by the end of the simulation, I just want to emphasize this is a log plot. So it's not that this initial jump is the entire story, but now I'm emphasizing where it is happening. There are particles that are essentially thermal energy. They get a significant jump at a certain point, and then they continue to fluctuate at higher energies up to, for this simulation, a Lorentz factor that is close to 10,000, not to 1,000.
Magnetization of this turbulence.
And for this one, actually, this is like a higher magnetization is 10. So 10 is the magnetization.
Jump is like when you see this here.
And the sigma is 10.
Jump like for this red particle. It's like.
It's very high.
Sigmas, yeah, it seems.
It's quite high above sigma. Indeed, let's say there is a bit of a statistical bias in selecting particles that get to the very high energy, because particles that get to the very high energy in general are a bit more lucky. So essentially, this is not the average jump. So these are more like average jumps here. So this is like a more lucky jump. That when you try to look at particles that get to the high energies, essentially you pick up those. So here I want to specify that indeed this process, as I see it, is like a two-stage process. One that is dominated at low energies by the non-ideal physics associated with magnetic reconnection, and one at larger scale that is dominated by the scattering on larger scale fluctuations. Just to make the previous statement about the injection more quantitative and statistical, now I'm showing you for all particles that we tracked in the simulation, I show what is the current density that is felt by the particles just at the moment where they get a significant increase in energy from the thermal pool. And this line is the red line in the probability density function of such particles that get accelerated, and in the x-axis is the current density felt by such particles with respect to the root mean square value. For comparison, the blue line is just an agnostic measure of the same quantity for the entire population of particles, irrespectively of particles being actively accelerated or not. And you can see that one is peaked at 0, as you will imagine, and with a tail that is a bit capturing the intermittency of the population. And here, instead, this one has a significant wings and is not peaked at 0. It means that particles that are actively accelerated from the thermal pool are feeling a disproportionately high value of the current density. And if you were to position where this is happening in one slice, for example, you would see that particles that are actively accelerated from the thermal pool, they are clustered around the current sheets. So this is another statement that is a statistical one that shows you that a thermal pool particle accelerated in those locations. And we can do another experiment that is the following. So let's add another population of particles in addition to the standard particles, the self-consistent peak particles. We add test particles that do not change the global solution, but now we remove the parallel electric field from the pusher of those particles. And let's see what kind of distribution they should get. So the red one is the particle energy spectrum of the entire population of particles, the self-consistent population of particles. And the blue one is the particles that were subtracted the parallel electric field. And you see that in the non-thermal tail, even if they can make a tiny tail here with a similar slope, there is a 2-order magnitude drop in the normalization. So it means that only in this case, 0.2% of the particle can make it to the first step. Of course, if you have a Maxwellian distribution, you can still find particles that are energetic, but indeed, missing this first step, it drops the normalization of the accelerated particle. So this is also another way to see that actually you needed to go through that first stage to populate the non-thermal thing.
This is particle cell simulation, so you are not explicitly exclude parallel like the IQ.
No, for the in reality, I'm explicitly excluding for the blue one in the sense that the red ones are the self-consistent particles that will inform the Maxwell equations, and so it will produce a self-consistent population. But in the same way you can add test particle in MHD, you can now add test particle in the peak solution that is informed only by the real particles. So this is another population of an equal number of particles that are not modifying the solution, are like passively moving around, where we can do the experiment. Yeah.
Yeah, I just really mean, like, can you expect some parallel, like in the center of the aging, not only the current sheets?
Oh, of course, there will be fluctuating parallel electric fields also in other regions, indeed. The parallel electric field that we care the most is like strong parallel electric field that is proportional and given by the reconnection rate. I didn't specify exactly, but indeed, if the reconnection rate were to be very low, like ancient theory, like sweep packet theory, so that will not have a significant effect. Here, the reconnection rate is high, and because of that, it translates on a high energization rate. So we, in this case, actually strong, let me add the word strong parallel electric field better. We can actually analyze also the stochastic part in the same way you could analyze from MHD simulation test particle and look at diffusive properties. And here, essentially, we take from 4 different populations simulation at different sigma. We consider, we measure directly the effective diffusion coming from the accelerated particles. And we see the diffusion coefficient in energy space, scale like gamma Lorentz factor square, so energy square. And we can look also how it changes in terms of magnetization, sigma here. And you see that it's linear. So we can build an effective diffusion coefficient in energy space that is given by this formula with a 0.1 coefficient that is given by the peak simulation. And if the stochastic process is a purely diffusive one, you will expect that the mean energy gain to follow this simple relation. And this, I just want to emphasize, is only the mean energy gain, because to understand the full evolution of the distribution of particle, actually the mean is not enough, and actually the process is not really simple diffusion. So, but to understand just the mean, we can take an effective diffusion coefficient and see how well it compares with what we see in the simulation. And here in this plot, we group particles by different injection times. So these are 4 groups of particles that are injected in different time beams. And this is the mean Lorentz factor. And we see that there are these 2 phases. One is the prediction, the first part is the prediction coming from reconnection, where Brec is the reconnection rate, and it is multiplied by the magnetic field that is felt by the current sheet. And the second one is the acceleration part. And you see that they match what we see here. We take also into account that the magnetization is time dependent, and we plot it here. A very important point is the following, that because there is this 2-stage nature of the process, where there is an initial energization along the field line and only later scatter, you can see that there is a significant effect on the pitch angle of particles. Here, F is the distribution of particles in terms of cosine of the pitch angle, where I remind the pitch angle is the angle between the velocity of the particle and the magnetic field, and in energy Lorentz factor here. You can see that if this was to be an isotropic distribution in pitch angle, this will have the same uniform color all across this plot. But you can see that at low energies, where reconnection is important, let's say low, depending with who you speak, actually this can be also significant energy. You see this strong red regions here that emphasize that most of the particles here are moving along the magnetic field lines. And as they increase their energy, actually, they become more isotropic, with actually a preference to move perpendicular to the field line, because the stochastic process of acceleration take advantage of the ideal MHD electric field that is perpendicular to the magnetic field. And so this gives some more pronounced anisotropy in the opposite direction here. With the few minutes left that I left, I want to give you a practical application of what turbulence can provide. And I want to go into the most extreme regime of turbulence, that is the relativistic turbulent regime. And I want to use it to explain the ultra high energy cosmic rays here. And there are very good statistical measurements that are being accumulated by Pierre-Roger collaboration. And this, I want to emphasize that there are some structures here that I can zoom here, and now I multiply the spectrum here by E squared and E cubed to emphasize some structure. I want to emphasize here that in addition to the anchor here, now you can see some other feature that here, like 4 or 5 years ago, this has been labeled like the in-step. Here is a new feature. Then there is again the suppression here, and we are getting to the point with the statistics. It start to be good enough to make some very refined data that can be tested against simulations, models essentially. And more important, actually, is the composition. That in the last few years, these are results of the composition from the previous year. They start to become incredibly well detailed, and they will allow us to make some. They start to become more constrained. And I will explain you now these plots for the ones that are not familiar with this business, essentially. On the basis of clearly, ultra-energy cosmic rays, they interact in the upper atmosphere, and they will produce a cascade of secondary particles. And the maximum development of the cascade depend on the particles that are incident. So lighter species can get deeper, while heavier species like iron, they will develop the cascade at higher values in the atmosphere. So you can, from that, consider what it is the mean of the depth of the maximum development of cosmic rays as a function of the energy, and there are predictions of how it should be based on some hadronic models that extrapolate what we see from the Large Hadron Collider to higher energy, because we don't have information from the Large Hadron Collider to the cross-section of such energies. And you can see that close to the ankle, most of the events are close to protons, here, this red line, and as you go up in energy, they get closer to iron. Even more importantly is the variance of that measure that show you that while at low energy, yes, there are protons, but there are also other species. As you go to higher energies, the variance of the X-max become very low, consistent with ions. That is telling you that the composition start to be very pure because the variance is small. So essentially, there are more and more pure elements as you go up in energy. So if you have an accelerator that spread particles across a given range in energy, you cannot make such a small variance. So you need to very precisely accelerate particles up to a given energy and nothing more.
But there is pretty large.
And they are getting lower. It's a good point. I'm going to show you that actually now they are large, but very constraining for models. So in the past, actually, we were not even able to say if at the higher energy they were all protons or not. Let's say until 20 years ago, most of the works actually were trying to explain the ultra energy cosmic rays with protons up to 10 to the 20 eV. And now it will be considered fully crazy according to the data. So actually the data is becoming quite good and robust. So now, let's assume that, for example, there is this shape of the functional form of what would be possible non-thermal energy tail of particles. That is like you have a power law, and it's very simple. You will see many phenomenological studies that you just consider an exponential cutoff that is almost a synonym of cutoff nowadays. And this is like inspired by, for example, prediction that, for example, come from shock acceleration theory. If you assume bomb diffusion, it will give you some functional shape like that. But I just want to try, this is not generic. It is what is often used when people do some phenomenology. You already see that it could be a problem because an exponential cutoff is a smooth cutoff. So it doesn't force particles to be accelerated only to a given energy. And by making smooth, it's very hard to accommodate a low variance of particles at large energies. And actually, to make it a bit more compact, people doing phenomenology have started to use a broken exponential. So you have a pure power law up to a given energy. And from that point, you start only an exponential one that kind of make it more compact and cut off. Even doing all these tricks, if you want to match the injected spectrum of the accelerated particle at the source, and then you can propagate those particles considering the interactions up to Earth, you will infer that the power law index has to be 1 in the case it is the steepest. You can be 0 or even above. So actually, for the ones of you that have some familiarity, actually something quite crazy, because you need something that is super hard And if you're familiar with plasma processes, there are no way with a plasma process to do that. There are some fine tunings that you can have. For example, there may be, for example, some interaction inside in your environment where they can actually select only a tiny bit of those particles, and that will kind of alleviate that factor, but that will be quite fine tuning because you just need the right amount of interaction in the environment to always select only a tiny bit of those particles, and you need also to repeat it for different objects and always at the same energy. So actually it's very hard to match it in this way. Luckily, if we actually run our first principle simulation of turbulence, we actually don't see that cutoff. This is like a simulation of relativistic turbulence. The magnetization sigma is much larger than unity. The flow velocity here is relativistic. And when we look at the accelerated particle here, I plot only the very tail, the very end of the tail here is multiplied by E cube, as you have seen in the previous plot. You see that there is cutoff here, there is a power law. Here the power law index is 2.4. And then it's a much steeper cutoff that is well approximated by this hyperbolic second to the energy square. And you can see that it doesn't match well at all with the exponential one that it overshoot. So here it's a mechanism that actually accelerates particles in a much more narrow range of energy. So that in principle, it favors the data that you have seen before.
What does the E-cut physically correspond to?
A good point, because this is the next slide. E-cut essentially is the cutoff energy that is given by this specific accelerator. And first I'm going to show you the scan, and this is the formula for the cutoff energy, essentially. The cutoff energy is like a criteria of being confined within the largest eddies, turbulent eddy in the simulation. As your Larmor radius get larger than the largest turbulent structure in the simulation, then you cannot be effectively accelerated anymore, and your acceleration process stops essentially. And you can check by changing using simulation with different magnetization sigma, that essentially means scanning the magnetic field square, and also the size of the coherence length at the outer scale of the turbulence LC respect to a plasma scales. And if you use in the formula in the E-cut the same formula that takes into account both the magnetic field and the coherence length, you will see that these cutoffs all overlap, essentially mean that they satisfy these relations. So essentially, it's a confinement criterion inside the larger structures. Even if you are still confined in the turbulent medium, if you go around, but still you cannot be accelerated anymore. If you use these, please.
So here you sort of had some control over the driving, which kind of sets the other scales, at least the E-cut. If you had some environment with the driving that was actually happening on a broad range of scales, that wouldn't quite be like this.
Good point.
That you have smoothed out.
Good point. If the driving involve a large range of energies, and let's assume scales, and let's assume that with similar power on those scales, then definitely it will broaden that. It's not going to be that way, and it's going to cover different scales. And that is going to be a problem to explain the observations. This is assumed that the driving has a characteristic scale where it peaks the energy. Very good. That's not all. The particles are accelerated within a certain turbulent environment, and while they are accelerated, there is not equal probability for them to escape it. So particles that have lower energies, they stay inside the turbulent environment longer. So the turbulent environment accelerate them, but also trap them. So particles that have, you can track the particles from the simulation and see how much time it takes for them to move to a certain distance from where they are at a given time. And you see that there is an energy dependent of this escape time, and you can see that it scales like energy to the minus approximately 1 divided by 3. This is not, it's a bit debatable, or at least the precise measurements is actually investigated. I think Philip is working on that. I've seen some slides from Jim that were discussing this sort of analysis yesterday. Anyway, if we take this value coming from peak simulation and we use also the previous values of the power law slope that we obtained for high sigma, we find that 2.4 minus about 0.3 give you a characteristic slope of escaping particle that is close to 2.1 in this case. And now let's, yes.
5 minutes.
I'm close to my endpoint, and I just want to now give you the what would be the prediction coming from a transport model in which now you can consider, let's say that you consider a source evolution now, and then you consider some sort of field, photon field around them, and all the interaction, relevant interaction, for example, photodisintegration of nuclei with photons, photopion productions, Bethe-Heitler processes, and so on, around the accelerator. Then you consider also during the transport that it goes through the extra galactic background light and also the cosmic and microwave background. You consider all these interaction, and then you check what kind of spectrum it occurs, we should be detected at Earth. And you keep it essentially the slope of the power law like arbitrary. You just impose the functional form of the cutoff that in this case is not anymore the exponential, but it's going to be the hyperbolic second. And you can see that with the hyperbolic second, actually, you get a desired slope in the accelerator that is 2.1. That is actually what we find with turbulence. So in this case, there are not any more extreme values of the power law spectral index desired at the source, but a common value of 2 actually fits the data. So this is, to me, is a high advantage of or at least is a smoking gun for which such a process could potentially be the physical process accelerating the ultra energy cosmic rays. And here is like the realization of the best fitting parameters for the turbulent accelerator model. And you can see here, here is the mass number. So in the red is like protons essentially. And as you go up, or at least color close to blue, you get heavier and heavier species. In yellow here is going to be helium. In green is going to be carbon, oxygen, and in green is going to be silicon. It's actually bracketed. There are different elements being in the same way. And in red essentially is iron. You can see that actually they will form that bump. But if you look below, here is the logarithmic mass number, both the mean and the variance. Essentially, you get the desired behavior that you have seen before. And the reason is that now the particles are accelerated in a narrow way close to the cutoff. And if instead you had to have a broader acceleration energy, essentially, by broadening the contribution of the different elements, you will not be consistent with the very low variance inferred from the data. I want to emphasize that actually these big boxes here are actually systematic errors due to our uncertainty in the cross-section that are extrapolated from LHC. But I just want to emphasize they are still very low, even taking into account these errors. So actually these trends are now very robust. These are data from the last year. I just want to emphasize that 5 years ago, the uncertainty was much higher. And so now we are starting to constrain that. So where do I will finish with this final slide. So where do we can we possibly find this regime of turbulence that is a relativistic one, so a turbulence that is high sigma? So here this is like a classic for the ones of you that are familiar, is Hila's plot. It's like a more colorful version of his original plot in the 80s, where it's plot like in the y-axis, the magnetic field strength, and in the x-axis, the size of the accelerator. You can take into account also the Lorentz factor if it is boosted close to you. And you can see which systems can potentially accelerate particles to those energy, because at least you need to confine particles where you accelerate them. And for example, if you want to make iron here, Fe, as we have seen, up to 10 to the 20 eV, you need to be at least covering this line, or you can be on the right side. You see the supernova remnant here are in the left side, so essentially they cannot reach those energies. But you see, you see a range of systems that actually can. So nature is conspiring against us. So the idea is to, with the physics, to start to remove some of these objects. Relativistic turbulence with such high magnetization can occur in this system like neutron stars and close to magnetars, but I will actually cross that because the cooling due to the very strong magnetic field actually will prevent that acceleration. It can be accelerated in low luminosity gamma ray burst, but also a high luminosity gamma ray burst in the prompt emission, as well as in tidal disruption event. And my favorite candidate would be low luminosity gamma ray burst. There will be others, but I will emphasize that actually the other place where we expect relativistic turbulence is from jets launched by AGN in what I would say the best location would be the blazar zone, but it doesn't need to be a blazar. Essentially, it can be also a radio jet. That if I plug numbers, actually, I will find it here. It is not emphasized this plot, but this would be my other bet where we can actually find the relativistic turbulent conditions such that they will accelerate particles to the cosmic rays. I had other slides, but those were more like a bonus. So we can discuss about the anisotropy in more detail, the anisotropy of the accelerated particle. I just want to emphasize one slide, if I can, that because big simulations show that actually the pitch angle distribution is not a constant, it's not isotropic, but it's not even a constant, but has a dependence in energy. If you take into account this fact in the standard formula that you will probably learn about Rebecki-Lyman or so, where you can relate with only the power law slope of in energy, what would be the synchrotron energy flux, for example, mu f nu, that is depending only on that. When you relax the fact that sine square alpha is a constant but depend in energy, and you redo the exercise, you will find that actually the shape is different, and if m is positive, as in this range here, actually the spectrum hardens. If it is negative, it's softened. So even claims like that the synchrotron emission could not explain spectra like, for example, gamma ray bursts because they are too hard and so on, they are not really true if you take into account that particles can be accelerated with a pitch angle anisotropy. So this actually changes a few things, and we can actually verify it also with particle in cell simulation. Actually, there are other things that can affect the general to decide that even the linear polarization degree actually change if you take into account the pitch angle anisotropy. So the standard isotropic formula is still great, but we need to remind always of the underlying assumption that typically doesn't hold if the plasma is strongly magnetized, because the acceleration of particles in a very strongly magnetized plasma typically imprint some preferential direction to the particles being accelerated. And with that, I will conclude, and thanks a lot for being here today, and I'm up to questions.
Anisotropy, you say that there is some height of the spectrum, okay, but for the turbulence realization, you have multiple current sheets with pretty much chaotic, especially delta V over B is about 1 meter. Then doesn't cancel the result of future anisotropy?
Great question, and indeed it is true. It depends on the value of the mean magnetic field. Indeed, as you say, there are different current sheets that have different direction. If there is a mean magnetic field, they will have a preferential direction. And just to give you an idea, it's a slide that I actually jumped on. This is like a turbulent with a delta V over B of order unity. So there is a preferential direction, and you get this signature. Imagine that you have delta B over B that actually is much smaller. So the mean field is smaller, like here by a factor of 8. You may see that there is this tiny imprint here, but then everything becomes isotropic. If you may recall, isotropic is essentially having a homogeneous color. So there is only a tiny imprint here that is the injection part, and everything isotropic. In the case where the magnetic field is very strong, so like here is 8 times the fluctuating field, like you may be in the loops, for example, from the coronal the coronal loops, or also you may imagine some loop coming out of a magnetar where there is a tiny fluctuating field. Essentially, particles are accelerated only along the field line. And in this case, actually, you keep the anisotropy all the way up. So, good point. Indeed, the level of anisotropy is dependent on the value of the fluctuating field with respect to the mean field. If the fluctuating field is very large with respect to the mean field, the scattering, the pitch angle scattering will compete with the acceleration and it will tend to isotropize that. Very good point. I think I have some other slides that maybe can emphasize that, but not sure. Maybe I have it only in the backup slides, I guess. No. About why?
And the question? Okay, the question we can get up. Yes, thank you, Luca. Thank you everyone for coming.
Thanks.